Okay. Can you hear me in the back? Ready? Okay, welcome to EE 123 lecture 15. Woo! Thank you, I appreciate that. Okay, we're still going to talk about sampling today. Okay, and in some way we're going to talk about sampling for some concepts of sampling for almost a week, next week. This week and then some of next week as well. Okay, so last time we talked about the ideal sampling model, so continuous to digital conversion, where you take continuous time signals and you convert them into digital samples. Okay? We tried to model this through certain modeling or simplifications, right? We took a continuous time signal and then we constructed this impulsive signal that represents something that looks discrete, however, it is continuous, okay, using impulse functions. Then we took those impulse functions and made them into discrete samples by just evaluating the function at equal number of samples. So we took the coefficients of those delta functions and evaluated them to get a discrete time signal. Okay. Then we went over the relationship between x sub z of j omega, x sub c of j omega, x sub s of j omega, and x eta j omega. Okay, the small j omega. Once we understood this relationship, we saw how what is the effect of the actual sampling of a continuous time signal. And if it's band limited, we saw that when we look at the Fourier transform, we get replication of our signal, but now those replications are not overlapping. Okay, if it's band limited, and we sample according to a particular rate. Okay. Then finally, in the last time, we talked about the ideal reconstruction, so converting digital into continuous time. And we showed that it's basically recreating the impulsive signal and then low-pass filtering it. Okay? Or taking the discrete samples and convolving it with a sinc, okay, with a sinc function. I showed you the case what happens when it's non-ideal in the terms of actually the... so what happens if we don't have exactly band-limited signals? We do anti-aliasing, okay? And if the anti-aliasing is not ideal, then we will get some sort of interference that comes into our signal, mostly at the edges, right? At the edges. So even though you are sampling and you are doing anti-aliasing filter, you have to understand that the outer edges of your frequency of your discrete time signals are contaminated with signals that you didn't mean that they'll be. Okay? So you always have to understand that. Okay? One of the ways to deal with it is actually to oversample. Okay? So then you can basically crop these away. Okay, so today we're going to talk about discrete time. Okay, so this is the plan for today. We're going to talk about discrete time processing of continuous time signal. Yeah, that's pretty trivial, right? We have a continuous time signal. We're going to sample it. We're going to do some processing and maybe produce another continuous time signal afterwards. Right? That's fair enough. Continuous time processing of discrete time signal. Now, that is kind of strange. Right? Why would you want to process something in continuous time when it's discrete? We'll get to that. And then if we have time, we'll see if we get to downsampling. I don't know. I have to gauge how long. But effectively, you'll see that when we talk about discrete time signals, and we're going to do some operation like downsampling or upsampling, it will be very much like sampling of continuous time signals, only slightly different. Okay? And the upsampling would be similar to a reconstruction, okay, from discrete to continuous, but somewhat different. Okay, but they'll have these analogies. We'll get to that. Any questions before we start? How's the lab? Everybody finished? Who didn't finish? Do you wanna take a 20%?
No, I didn't know the files have changed. So
Oh.
old versions, and then I couldn't get anything. I thought my code was wrong.
Okay.
Today,
Okay, you can submit it then. That's fine. If it's our fault, then it's okay. Okay. But everybody else were able to? You got planes? Just one? Oh. Okay, but one is pretty good too. Oh yeah, you could see it. Oh, that's cool. Oh wow, that's awesome. All right, great. Are you enjoying them, the labs? Yeah. There's way more really nice ones coming up. Sweet. Okay, so reconstruction. Let's quickly go over this. We went over this before. When you have this, the Nyquist sampling theorem says basically that if your signal is band limited and you're sampling at a rate which is higher than twice the highest frequency, or you're sampling at a rate of the bandwidth of the signal, then the signal can be uniquely determined from its samples. And the reconstruction is through either a low-pass filtering or a sync-type interpolation. Band limitedness is the key. It's the fact that I can combine, put continuous time signals between those discrete points in a way that is band limited. Because there's other type of signals which are not necessarily band limited that can fit there, but there's really just one that is band limited. In the frequency domain, effectively, we're constructing this impulsive signal, which gives us a Fourier transform which has these replicas. Once we filter with an ideal low-pass filter, we get back the spectrum that we started with. Okay. In the time domain, it's a convolution with a sink, where our signals, each one of those coefficients of our signals, basically you put it on top of shifted, scaled sinks. So sink, 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 sink. The cool thing about this, it's guaranteed to be band limited because it's a sum of sinks. Sinks are band limited. We're linearly adding, or a linear combination of shifted sinks. It has to be band limited. Okay. Nice thing, property of a sink also is that it has 0 whenever the other samples appear. Okay. So that's the cool thing. The problem with this, though, is that if you want to reconstruct a signal, you have to have an infinite evaluation of that signal, because the sink has I need to basically convolve with something that is infinite. Okay, so that could be a problem. Often, if we want to reproduce something, then we would do it over a finite time. If you think about a machine, for example, that would do it like an A to D, what I could do is have various sinks that are basically infinite. And then I just start adding coefficients, and then just playing those sinks, right? One at a time. So you can think of a machine that produces a sink that's centered at 0, a machine that produces a sink that's centered at 1, and so on and so forth. And you just put a voltage on them, and then let them play. Okay. So that will be a digital to analog. But of course, it's not great, right? Because it has infinite support. So I'd like to do something that sometimes has finite support. Okay. Great. So let's talk now about discrete time processing of continuous time signals. Okay. So here's what we have. We have a continuous time signal gets into a discrete time system. Or in fact, this is a continuous time system. Right? This is a continuous time. It continues here, continues here. In this continuous part, we have a continuous to digital conversion with some sampling rate T1. Then we have a discrete or a discrete time system. In this case, we're going to assume that it's LTI. Why do I assume it's LTI? I've written here something that by definition makes it an LTI. frequency response. There is no frequency response for something that's not LTI. Okay? So it has to be an LTI system. Okay? So I have a LTI system here, then discrete to continuous conversion with a maybe different sampling rate. Okay? And then continuous. So the question is, if h of n is LTI, so h eta j omega exists, is the whole system LTI? Always. No. Who said no? Why?
Because you cascade with something that isn't LTI, then that's
Well,
not necessarily.
Well, this is LTI, the mill.
Yeah, but the continuous analog or continuous discrete not necessarily.
Why? What makes it not LTI there? The sampling. Is it? Maybe. That's not actually not necessarily a big problem. Yeah. Could be a problem, but not necessarily.
You have to be sampling fast enough.
What if I had aliasing? Then I would generate new frequencies. That's definitely not LTI. Okay? That's definitely not LTI. So the answer is yes, if x of c is band limited by the sampling rate, then in that case, if we look at the effective frequency response of the system, so we take the output divided by the input, then in that case, the effective frequency response is h eta j omega, where omega equals capital omega times t, within the frequency of omega is less than omega s over 2. So within the bandwidth of the sampling. Okay? So if it is band limited and we don't have aliasing, yes, then it is LTI. So in that case, if we have, for example, a length 5 moving average, okay, for a length 5 moving average, we have a magnitude response which looks like this. Okay? Then the effective magnitude frequency response will be the values of this function between minus pi and pi corresponding to omega s over 2 to minus omega s over 2 to omega s over 2. Okay? And outside is going to be 0. Why is it going to be 0 outside? Band limited. That's how I reconstructed. When I reconstruct, I do a low-pass filter, right? So it doesn't have any frequencies outside. Okay? When I reconstruct, it's band limited. Because I go from a D to C. By definition, that makes it band limited. Okay? All right? Does this make sense? Okay, great. Excellent. So now there's the other weird thing that I was talking about before. That's kind of strange. I really don't get it. What's the purpose of this? Continuous time processing of discrete time signal. Let's see. You put x of n, you make it analog by taking digital, convert that into continuous time. You've got x sub c of t. Then you plug in some, capacitors, resistors, inductors, whatever. Get something out, then sample this, and get back digital signals. Okay? So is this LTI? If this is LTI, is this LTI? Yeah, it's always actually going to be LTI. Okay? And I'll show you why. But what's the purpose of this? The purpose of this is not to build this. Okay? The purpose of this is wholly to understand certain digital systems that it's hard to understand what they do in discrete time, but once we make the connection to a continuous time signal, we understand more of what is actually going on in those systems. Okay? So it's just as a tool to understand and interpret particular digital systems. And I'll give you an example of what I actually mean. And it will blow your mind away. I'm not sure actually blow your mind away. But it will be close to blowing your mind away. That close. Or that. Or maybe a little bit more. Depending on the person. But if you're mathematically inclined, it will blow you away. Okay. So I want you to recall that basically x sub c of t is a shifted sinks, right? That are scaled by x of n. And they're shifted by t. Okay? Multiples of t. Okay? So here's what we're going to do. We're going to try to figure out basically what's the relationship between hc j omega and the whole h e to the j omega. Okay? And understand what they mean. Okay, so bear with me here. Okay? Again, I'm not writing on the board, so I'm going to go at a rate as if I'm writing on the board, just so you get this. So x of c j omega equals to, what is it? Okay? What it actually is. Because I go and reconstruct, right? I'm going to reconstruct something that's into a, so I have something from minus pi to pi. That part is going to basically become a band-limited continuous time signal. Okay? Something that is discrete. I can describe it using a discrete time Fourier transform from minus omega to omega. That will go and become a continuous time signal from minus pi omega s over 2 to omega s over 2, band limited. Okay? So this is what it's going to become. It's actually this, right? And we multiply by capital T to compensate for the scaling. Okay? If you remember in the reconstruction filter, the low-pass filter had a magnitude of capital T. So it's capital T x e to j omega, where omega is capital omega times t. Okay? And that is only true if your capital omega is between omega s over 2 and minus omega s over 2 and omega s over 2. Okay? So it's band limited. Okay? Can I move on? Yeah? Okay. Great. All right, so what is y? Remember, y is the output, right? This one. So that's before, that's continuous, and then I do the continuous time processing and then continuous signal. So what is y c j omega, the continuous one? It is x sub c j omega, which is this, multiplied by h c j omega, which is the analog, right? The analog frequency response. Let me argue that it's band limited no matter what the impulse, the frequency response is. No matter what it is, it's still band limited. So give me a non-band limited frequency response. I don't care. The product is always band limited because this guy is band limited. That's why aliasing is not going to be an issue. Okay? So this is always band limited. Great? So in fact, if you think about the effect, this is only going to affect this where it's within the bandwidth. Okay? So I can design many continuous time signals that will do exactly the same thing, theoretically. Okay, so now the digital that comes out is really replication of this. Right? When I sample, I replicate. Right? So whatever is between minus pi s over 2 to pi s over 2 should be replicated. Okay? And so what I get, right, is 1 over t yc of j omega, whereas omega equals omega over t. The thing is that there's no replication because this was band limited. So when I sample, I just get basically minus pi to pi. Okay? Within the same bandwidth. Okay? So there's no replication. If I put it all together, I get y e to j omega equals to hc j omega, where omega, capital omega is the small over t, multiplied by this, and that's only for omega is less than pi, because it's not defined outside omega, outside of pi. It basically is repetitive. And I'm going to call this h e to j omega. Okay? So now I have a way to translate between hc j capital omega to the discrete time system that represent the exact same thing. So, in fact, if I did this process and I use hcj capital omega, so the continuous time system, to be between omega s over 2 and minus omega s over 2 to omega s over 2 to be something like this, and outside is going to go crazy. Like crazy. Thing is, I don't care. Right? I don't care. It doesn't matter. Because this is multiplied by a signal which is going to be 0 out there. So it doesn't matter. So my effective e to j omega is just the value of that function between minus omega s over 2 till omega s over 2. Okay? So that we're going to find useful. But that's exactly what the whole discrete time system is going to be doing. And I can plug in whatever I want. Now, Mickey, why are you doing this? Why are you doing this? This is like, it makes no sense still, right? Makes no sense. It's going to make sense in a second. 21, 22. Okay? Let's look. I mean, so far, when I put a linear phase across your spectrum, right? If I multiply your frequency domain, if my frequency response will be e minus j omega delta, where delta equals 1. Okay? If delta is equal to 1, that is a sample delay. Right? Because a shifted discrete impulse function will give you this with 1. If delta equals 2, then it's a 2-sample delay. But what is half-sample delay? I don't know. Right? I mean, how can I take 2 samples and I move them by half a sample? What does it mean? Right? Now, we're going to go and try to interpret, because we had, maybe our signal was continuous at some point, and we sampled it. Let's see what it means, how it affects the continuous time signal, and then we're going to sample it again. Do you see where I'm coming at? That is why it's important to interpret it that way. So let's see what happens. I mean, if I do half a sample delay in the continuous time, does it make sense? Yeah, it makes perfect sense to you, right? Perfect sense. But what is half a sample delay in discrete? Well, I'm going to show you that it is actually going to be exactly the same as half a sample delay in continuous time, if we're going to do this. But there's implication to this. Okay. So what is a time domain operation when delta is not an integer? Okay. So what we're going to define then is we're going to define the system to be e minus j capital omega delta t. Okay. Where delta t is a certain delay in time corresponding to half a sample. Okay. So now we have x of n. We continuous time reconstructed. We delayed by delta t, right? By a certain delta t. And then we sample it again. That makes sense. Right? That makes sense. Great. So that's exactly what we're going to do. Okay? The thing is, you really don't need to implement this. It is useful to understand it, but you'll see it's all discrete system. It's going to end up to be a discrete time system, but the interpretation is as if I reconstructed, as if I did all this stuff and then resampled again. Okay, we're just not going to do it, but we're going to interpret that way. So a non-integer delay is I have some samples over here, right? And this is x of n. Okay. Now, what I'm going to do is I'm going to reconstruct in continuous time. Then I'm going to resample it with a delay. Okay, those are the blue ones. And now I'm going to assign this to be n equals 0. And that will be the output. Do you see that it's delayed? It is delayed. Are these the exact same samples? I mean, there's something in between, right? I did some form of an interpolation by doing that. Okay? But I start with something discrete. I end up with something discrete. Can I just not go through the continuous and do everything in discrete? Yes. The answer should be. Right? But it was a rhetorical question. Obviously, you could do this. Right? If something is discrete, end up with discrete, why shouldn't be? Okay. So, if you think about the block diagram, is really interpretation, right? So YC is really just a shifted delta of our signal, and then Y of n is sampled version of that shifted signal. What is the shifted signal? Is x sub c nt minus t delta t, right? It's the evaluation at n, every t time, right? I evaluate that function, but then I shift those evaluation by some fraction of t, okay, maybe half. But wait a second, I can write this in terms of x of k, right? This has a really nice relationship to x of k, the x of n, the digital one, right? Is because if I took x of n and I convolve it with a sinc, that would give me that. So I can just write it as a sum of shifted sincs, weighted shifted sincs. That's exactly what I'm doing now. I'm summing over x of k multiplied by sincs, which are normally t minus kt over t, but now I shift them by t delta. Okay? That's the fractional part. That's when I evaluate for t equals nt, right? So I take the continuous time sinc and I evaluate this t at times n times t. Okay? This is the continuous time, and I'm going to evaluate it because that's exactly what I'm doing, evaluating it. If you have n times t, k times t, t times delta divided by t, the t's don't matter. The sampling rate doesn't matter. It makes sense because I already have discrete samples. As long as I don't reconstruct something without creating aliasing or removing information, it doesn't matter if I use the really fine delta, t or like a relatively coarse t. It doesn't matter what t is, because I perfectly reconstruct my continuous signal. So those t's cancel, and then I basically get x of k of k sinc, n minus k minus delta. Okay. So now, when I have a fractional delta, a delta is not 1, it's not an integer. It's really like convolving with a sinc. Is taking my signal and then having those as shifted sincs, as a shifted sinc. Okay? So here's an example. Let's say h of n equals sinc n minus delta. Okay, this is really the impulse response in this case. Let's say delta is equal 0. When delta equals 0, then sinc of n is just a Dirac function, a discrete Dirac function, because it always cancels for n not equal 0. It's only 1 for n equals 0, but it cancels. Doesn't this blow your mind? Like, whatever was delta, now it's a sinc. Right? There's no Dirac function anymore. It's a sinc function that you are always sampling its zero crossing. But it kind of makes sense because we're dealing with band-limited signals because we sample anyway. Right? When we sample, we kind of assume that our signal is band-limited. If we're thinking about a perfect reconstruction in continuous time, it's always band-limited. So it's always, a Dirac should always be, I mean, I can't really sample a Dirac function. It's not band-limited. A continuous Dirac function I cannot sample, right? And be band-limited and be able to represent it. But a sinc function I can. So this is what it is. And whenever I have a certain delta, right, this is basically just a zero crossing. But if I have a certain delta, what I'm doing effectively is evaluating this sinc function at different points. So now, if I shift by half, I'm going to get a lot of coefficients. Okay? So for every non-integer delta, I'm going to get a lot of coefficients. Does this make sense? Has to make sense. So understand, when you have delta, discrete Dirac function, they're really representative of a continuous time sinc. Okay? If you shift it by half a sample, now you're going to evaluate that sinc at not at the zero crossing, so you're going to get a lot of stuff going on. But always remember that in the back of your head. That's exactly what we're doing. So half a sample delay, quarter of a sample delay, it's always going to give us these extra coefficients suddenly, because now we're not sampling exactly on the zero crossings. Okay? This is why it's useful to do this kind of analysis. It's useful, again, if you do upsampling and downsampling. It's useful if you do interpolations of all sorts to understand what does it do to the continuous time signal. Okay? So this is a really useful tool. Any questions up to here? Exciting, huh? Who'd have thought a Dirac is actually a sinc? Crazy. Who shared my thoughts? Do you? Natalie? Yeah. All right. Okay. So now I think we're ready to teach you some of the most useful tools that you've ever, like if you've taken this class, now it's going to become super useful. Why? Because we're going to talk about changing the rates of signals in discrete time. Okay? Why is it useful? Because you have to do that all the time. Somebody gives you something that is sampled at a certain rate, and it just doesn't fit you. You need to change the rate. How do you do this? Okay? Now, you can use MATLAB resample. Okay? But I think you need to understand what it's doing because it's not necessarily doing something optimal for you. Okay? So it's really useful that you understand what are the trade-offs. When you write resample, what does it actually mean? Okay? Changing the sampling rate, it's never going to be ideal unless you're going to use perfect filters, which are going to be infinite impulse response. So there's going to be some implication about changing your rate of a signal, especially if your signal is small and you want to change your rate. There are going to be all sorts of edge effects if you're using large filters. Okay, so you've got to understand this. The first thing that we're going to do is downsampling. Okay, where does this come? You're going to see in Lab 2. You're going to sample at 240 kilohertz. 240 kilohertz. That's what your SDR is going to give you. You're going to do all sorts of processing. You're going to get audio at the end at 240 kilohertz. Now try to give your computer samples at 240 kilohertz to play. I bet it is going to be upset. Really upset. So upset that it's not going to play. it will be really much more comfortable if you're going to go down and present the samples at 48 kilohertz, or 41.1 kilohertz, or 24.05, or something like slower. Otherwise, it's going to really be upset. It's too much. I don't want to deal with this. My hardware is not ready for that. It's not going to work. So you'll have to downsample. Okay? As it turns out, when you do downsampling, it's similar to continuous to discrete conversion. You're going to expect similar effects, like aliasing and mitigating with aliasing by anti-aliasing filters. Okay? And if you think about this conceptually as an engineer, what is the finely sampled signal? I mean, okay, sample here, 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 and here. Is that continuous? No, right? So, but what about here, 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 here? Is that continuous? What about is that continuous? Still samples. At some point, right? For an engineer, it looks continuous, right? So in that case, downsampling would be like sampling that continuous signal, right? In some sense. So let's go over it and see what is the math behind it. Where should we really be worried? Okay. What is that? Okay. Downsampling. We start with x of n, m, n, x of n. We're downsampling by a factor of m. This is a compressor operation. It chooses every mth sample. Is that shift invariant? No. Is that, what else? Well, what properties? Is that linear? Is that memoryless? Is it memoryless? It's like the first lecture slides. It's not memoryless? Why? You have to store. I mean, like you're outputting and sampling samples at a certain rate, but you're getting more, right? So you have to wait. Okay, so the output is not, is dependent on some past. Okay. So you have to have some storage. Okay, so we're going to decimate. We're going to get xd. D means decimation, which is really the evaluation of x at n times m. Okay, that's what it is. So you can also, in the back of your head here, think about it as samples of here n times some t, and here will be n times some mt, which is a certain different rate of sampling, right? That's what it really is. It's a different rate of sampling. Okay. So of course we're going to get some effects of aliasing maybe or something like this, because we're actually sampling, if we think about the continuous time, again, as something that might not fit within the Nyquist criteria. Okay. So what is the DTFT of x e to the j omega? Is really shifted versions of x of c. Okay? We shifted by omega s's, right? Which is 2 pi over t. Is exactly the same thing. Okay, so I have a certain bandwidth of my signal, and then I replicate it every omega s frequency. Okay. So what is x sub d, e to the j omega? Is exactly the same thing, only now I shift by mt. Right? Sorry, by that. 1 over mt, which is omega s over m, right? Omega s over m. And it's scaled a little bit differently too. Okay. So, yeah, that's great. Excellent. But I'd like to bypass the use of x sub c, the continuous one. That's the one that I used before. Right? That's, again, it's the same continuous time processing of discrete time signals. But I'd like to avoid that and go directly from x e to the j omega to x sub d e to the j omega. So what I'm going to do is I'm going to look at this, and it sums over k. Where's r? I found a typo. Well, really what I'm going to do, it's not really a typo, but you see this counter that goes from minus infinity to infinity? I can count differently. You can count from minus infinity to infinity by going 1, 2, 3, 4, 5, right? With one counter. Or you can count with two counters. One counter goes from 0 to 9, and the other counter basically goes and skips, right? So we could do that. So what I'm going to do now here is substitute r into km plus I, where I goes from 0 all the way to m minus 1, and then k goes from minus infinity to infinity. Okay? You can think of it as kind of hours and minutes. Okay, clock. So if I have this is the usual thing. I'm going to break it into two sums. Okay? Two sums. One sum goes from I equals 0 to m minus 1. And the other sum sums over to infinity. Right? And then we have, yes. And then we have this, I have to add this I here to skip. Right? That's where I skip. Okay? So this is exactly the same thing. But wait a second. What is actually this? If I look at just this part, oh, look at this. Okay? If I look at this, just this part, this looks awfully similar to x e to the j omega. X e to the j omega has omega over t and 2 pi over t. Here I have omega over mt, 2 pi over mt. Right? Sorry, 2 pi over t. Okay, right? It's just I have this m here. So this is effectively x e to the j omega over m minus 2 pi over m times I. Okay? Instead of xc. If I do that, then I get that x sub d e to the j omega equals to 1 over m, and then the sum over I equals 0 to m minus 1. So just the sum over, how many downsampling I'm going to do, of e to the j omega over m minus 2 pi over m I. What do I get really here? Okay, so here's the point. Okay, there's two effects here. When I downsample by a factor of m, my signal stretches by m. And then it's replicated m times. Okay? That's what it does. Yeah. So here's how it works. Let's say I have a signal that its DTFT looks like this. It starts from minus pi over 2 to pi over 2. And now I downsample by a factor of 2. Okay? If I downsample by a factor of 2, I stretch it by m equal 2. Okay? That's what it says, stretch. Okay, so I stretched it. But then I need to shift it by nothing, which is I equals 0, and by pi. When I equals 1 and m equal 2, I get a pi here. Okay? So this plus another version that's shifted by pi. I mean, the thing is that this cannot be a DTFT. Why it cannot be a DTFT? It's not periodic with pi, with 2 pi, right? Now it is. It will always be. Because it is a DTFT, so it has to be periodic by pi. So what I get is that this stretches, right? Now, it kind of makes sense. Why? Because if I downsample by a factor of 2, I have half the bandwidth, right? So now my samples represent half the bandwidth. If I had empty bandwidth over here, now all the samples have to represent the entire bandwidth. So this thing effectively stretches to minus pi to pi. Okay? If I would have sampled my signal at half the bandwidth, then it would have been exactly that. Okay? This, what happened here, that I oversampled by a factor of 2, because I have empty spaces. I could have sampled at a lower rate. Right? 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 Yeah? Yeah. So here's the problem. Why if I now downsample this by a factor of 3? Okay? So scale by 3. What? Yeah. I scale by 3. And then I shift by I equal 1 multiplied by 2 pi over m equal 3. And then by I equal 2, 2 pi m equal 3. Okay? Now I get aliasing. Okay? It kind of makes sense. There's really, if I downsample this by a factor of 3, there's no way I can represent everything. It's like originally I would have sampled at a 3 times lower rate. Of course, it doesn't fit the bandwidth. Okay? So remember how it would have affected a continuous time signal. Now, the other way to think about it is that basically, instead of doing all those replicas and stretching, and the thing stretching and then replicating, just basically take each of these replicas and then stretch them around themselves. Right? That's exactly what's also happening. Okay? So just take this and stretch it, and then take this and stretch it. It will come to exactly the same mathematical result. Okay? So that's another way of thinking about it. Okay. So that is a problem. Right? If I want to downsample by a factor of 3, that's a problem. I need to do something about it. So I don't get aliasing. What do I do? Low-pass filter, where? What? Between negative pi. Okay, so I low-pass filter between here and here. That's not useful. That's not doing anything. Pi over 3. That's right. Because what would happen after I downsample, whatever was pi over 3 will become pi. Okay? So, check this out. Multiply. Huh? Okay? And then stretch. That's basically it. And so, in the lab, you're going to have a 240 kilohertz signal. You're going to end up with 48 kilohertz. That is a factor of, right, 5? 5. Factor of 5. What will you need to do before you downsample? You're going to low-pass filter, because you're going to have a lot of crap in the other frequencies too that you want to get rid of. Before you downsample, you're going to have noise. You're going to have other, it's going to be an FM, so you're going to have the stereo and the pilot and all the other stuff is going to be in the high frequency. That's not good. You're going to filter, and then you're going to downsample. And you're going to see how beautifully this all looks like. Okay. Any questions? Okay, I'll see you on Wednesday then.